Okay, so we would like to show here that the statement that the limit of pi of x over log x, we recall that, of course, that pi of x is the amount of primes that do not exceed x. Is equal to 1 if and only if the limit of theta of x over x is equal to 1. Again, we recall that theta of x is the Chebyshev function. Okay, and this pretty much tells us that the statement of the prime number theorem translates to a statement about theta of x over x. What would like to recall is that none of these limits is even known a priori to exist. Of course, once the prime number theorem is shown, both limits are shown to exist. But this pretty much tells us that in order to prove the prime number theorem, we can just work with the Chebyshev function, and one can work with either of the two Chebyshev functions, and both of them appear in different groups of the prime number theorem. So let's recall that this statement is indeed the prime number theorem. So if we show this equivalence, then the other statement will also be the prime number theorem. So the first thing that we can see here is that theta of x, which is the amount or the sum of the logarithms of prime numbers that do not exceed x, is less than or equal. So replace all these logarithms. This is a very crude statement by log x, since p doesn't exceed x, then its logarithm will not exceed the logarithm of x. And how many such primes do you have? The answer is pi of x. So this is less than or equal to pi of x over log x. And so this means that theta of x is less than or equal to pi of x times log x. And if we divide both sides by x, then we get that theta of x is less than or equal to pi of x times log x over x, which, by the way, this is the same thing as pi of x over x over log x. So, we're going to treat them as the same. So this tells us right away that the lower limit as x tends to infinity of theta of x over x is less than or equal to the lower limit as x tends to infinity of pi of x over x over log x. And same thing for the upper limits. Okay. So now basically we will want to prove the opposite inequalities. And this, if we manage to do that, so if we manage to show that the left-hand side of the first inequality is also greater than or equal to the right-hand side, and same thing for the second inequality, then we will show that these upper limits and lower limits that do exist are the same, which means that if the prime number theorem is true, then the limit of theta of x over x should be equal to the limit of pi of x over log x, because the corresponding functions here have the same upper and lower limits, and vice versa. If you manage to show this limit, that this limit exists and is equal to 1, then you can show the prime number theorem. Okay, so the question is, how do we show the reverse inequality? And there is this very nice little trick. And the trick is the following. So start by fixing a number A which is between 0 and 1, right? Let's fix such a number. Okay, we really want to create a sort of lower limit. I'm sorry, a sort of lower inequality for the logarithms. So we can certainly say that the logarithms, the primes that are between x and x to the a, so a is a number less than 1. So let's actually take strict inequality here of log p. This is precisely theta of x minus theta of x to the a, right? And here we can have a lower limit for this, so we can say that there's a lower bound for these logarithms, and this lower bound will be the logarithm of x to the a. And how many such numbers do we have? We have pi of x such numbers, and from them we have, so let me give myself a little more space here. So we have pi of x such primes that are less than or equal to p, and from those we have to subtract as many primes that are less than or equal to x to the a. And here we can take a logarithm of x to the a. Okay? So now what we have is that pi of x, let's rewrite this inequality for a second. Because you can see that this is pretty much moving in the opposite direction than the one we had before. And now let's actually divide through everything by x. Okay, and let's see what happens. So first of all, let's start with what we have on the left. Okay, so start with this. Theta of x to the a over x. So this is, roughly speaking, less than or equal to the amount of primes that do not exceed x to the a times the logarithm of x to the a divided by x. And now, because of the properties of the logarithm and the fact that the amount of primes that do not exceed x to the a is at most x to the a, we will have this. And now you can see what is happening. So this is the same as a times log x over x to the 1 minus a. And the logarithm increases slower than any positive power of x. And this is certainly a positive number. So this whole thing goes to 0. Okay, so in other words, this component here goes to 0. And for exactly the same reason, if we take this component over here, that also goes to 0. Okay, it's exactly the same kind of reasoning. We already showed that this thing is less than or equal to this, which is precisely what we encountered there. So in other words, if we want to understand what is going on here, is we have a pi of x over x minus pi of x to the a times logarithm of x to the a over x. So I'm sorry, this one here, I should have multiplied also this by logarithm of x to the a. So pi of x times logarithm of x to the a over x. And this is less than or equal to theta of x over x plus theta of x to the a over x. So now when we consider sequences for which these functions have the behavior that we like, meaning they tend to the upper and lower limit, these corresponding components of these sequences tend to zero, which means that they have no contribution whatsoever. And what this really means is that for these terms right here, which is all that matters, we will have the corresponding inequalities, meaning the lower limit of pi of x times logarithm of x to the a over x will be less than or equal to the lower limit as x tends to infinity of theta of x to the x. And again, I'm saying because these notions are based on the choice of specific sequences, and for those sequences, the two encircled quantities tend to zero, which means that eventually they're not going to contribute anything. So, however, the limit on the left is by the properties of the logarithm, a times the limit as x tends to infinity of pi of x times logarithm of x over x, which is less than or equal to the limit as x tends to infinity of theta of x over x. So, in other words, we can say that this limit is greater than or equal to this limit times the number a. And remember, a is allowed to be any number between 0 and 1. So what we do here is we let a approach 1. And what that gives us is that the lower limit as x tends to infinity of pi of x times logarithm of x over x is less than or equal to the limit as x tends to infinity of theta of x over x. What we did with the lower limits, we could have done with the upper limits, and thus, if you check here, we obtained the reverse inequalities from what we had right here. So if we put everything together now, what we get is that the limit, the lower limit, which exists, of course, as x tends to infinity of pi of x times, or let me just write it as pi of x over x over log x is equal to the lower limit of theta of x over x. And same thing for the upper limits. Okay, so now the reasoning is complete as following. If the prime number theorem is correct, then this means that this lower limit is the same as that lower limit, and they're both equal to 1, right? Yes, but then that would mean that this limit is 1, that limit is 1, and the limit of theta of x over x exists and is equal to 1. Conversely, if you know that the limit of theta of x over x is equal to 1, then this means that the lower limit and the upper limit are equal to 1, which means that the corresponding lower and upper limit of the function pi of x over log x exist, or they're also equal to 1. They exist, and therefore the limit of pi of x over log x is equal to 1, which is the prime number theorem, which again, this means that the prime number theorem is equivalent to the limit as x tends to 1 of theta of x over x being equal to 1. One can show it's pretty much exactly the same type of argument, that this is equivalent to the limit as x tends to 1 of psi of x over x is equal to 1. Again, we recall that psi of x is not just the sum of all the logarithms of prime numbers, but rather for any prime power that does not exist x, we take the logarithm of the corresponding base. So that's all, and these are pretty much the statements that can be proven. These are the statements that one establishes in order to establish the prime number theorem. Thanks for watching.